So in the previous lecture, we talked what happens when we have a source and a uniform flow. Here, we're going to have both. We're going to have a source and a sink all together. And we want to understand what happens to the uniform flow of your problem. So in general, what you will have is something like this, where you got flow coming out and you got a flow going back in. That's why it's called a sink. So uh, let's consider a case like this. This is a simulation. In this simulation, you're going to see we're going to have a sink. This sink is given in the middle, and we're going to have a uniform flow coming. And look how the uniform flow comes around that. Okay? So this is the case that we did in the previous lecture. Now what we're going to do is we're going to add a source, and we're also going to have a sink all at once. Okay, so now let's see what happens when I have the same uniform flow that's going to come around this. And you can see what's happening here. You have one side that's the blue represents the source, the green represents the sink, and you can see what it's actually trying to do, right? If, so the idea here is what we are really very much interested in this problem is to see and understand what's the behavior, what's the velocity at all these points, and what this type of figure that this generates. Okay, so let's suppose we have the cylindrical coordinates in x and r direction. So this is x and this is r. Okay. And then the uniform flow in your problem would be, so your uniform flow, the potential velocity in the uniform flow will be u infinity x, because I'm going in the x direction, not z. And if I replace that, I get r cosine of theta. Okay, and then your total source, the potential of the source will be minus q, we derived this last time, okay, plus r, the distance to the source. Now if I want to know my sink is exactly the same expression. The only difference is it will be positive, because now my strength is negative is inverse of what's happening to the source. Okay? So if I had this case, and now I wanted to arbitrarily think that I want to see what happens at the point P, let's say, in the body, right? And this is the source, or this is the sink. And so you can immediately see, and this is distance at minus a, this is as distance a, then you can see that your R source is actually equal to R squared, right? This R squared plus a distance x plus a squared, okay? So your R sink then will be nothing else than R squared plus x minus a squared. Okay, and we know we derived this last time that a in all our problems would be 4 over pi. So anywhere you see a, just know that you're going to replace it with this value. Okay, so if I want to find what the total flow is in my problem, then the flow potential, the contribution of my uniform flow, my source flow, and my sink flow, then now you can say this whole thing is equal to u infinite x plus the source will be minus a square root of x plus a squared plus r squared, and this will be plus a square root of x minus a squared plus r squared. Have to be very careful with the plus and minus. These are not identical terms. I have a plus here and a minus there. Okay, so if I move on to the next page now, and I want to find what is the velocity in the x direction, okay, remember that could be z if you're working in the polar coordinates were defined, or cylindrical coordinates were defined in z and r. Okay, so if I take the derivative of this term respect to x, you can show that your term becomes a, the whole parenthesis. So this is x plus a, and this becomes x plus a squared plus r squared 3 over 2 minus x minus a, x minus a squared, this is squared, sorry, not squared, close the parenthesis, plus r squared 3 over 2, okay? And then your UR, that's partial of phi respect to R, will give you A R x plus a squared plus r squared 3 over 2 minus r x minus a squared plus r squared all over 3 over 2. Okay, so this is the expression of UR that I have. It's very interesting to know what it really does. If you evaluate this expression, you can see that the value of u over this, the value of u over this region right here, okay, this region right here will be positive. Anywhere in, as you're going along to the stream, will be positive. Anything between your sink and your source and the stagnation, these are stagnation points. Remember, your stagnation point is a location where your velocity is equal to 0. Okay, so this velocity is equal to 0 at the stagnation point. Now UR is also equal to 0. So your total component of velocity is 0. Okay, so at between the stagnation point and this point, your U will be minus, negative, and anything inside here will be positive, because there's a uniform flow coming in this direction. Okay, so that's important to keep in mind. So now, as I keep on moving on, now that we kind of to understand how this comes about, this, right? So let's go ahead and understand what the expression u of x does. So if I use the expression, okay, and u of x at x equal to 0 and r equal to 0, so I'm basically trying to find my stagnation point. And I take this expression now, I put x equal to 0, r equal to 0 in this whole expression. You can show that the expression, then what you will get, your expression of this expression right here will be following. Okay, so this is 0, this is 0, this is 0, 0, 0, 0, this is 0, 0, 0, 0, 0, 0. So immediately you can see that UR will be 0 because all of this is 0, right? And then this expression right here, when this is equal to 0, this gives you, this whole expression gives you a over a cube minus minus a cubed. This whole thing is going to give you 2 over a squared. So that means that this expression will be nothing else than u infinite plus 2a over a squared. So the value that we found is this value right here, okay? The value right here in the center, that location, we are able to show that UR is equal to 0 and U of X was equal to U infinite plus 2 times A squared. So that's the value right here, okay? So now the next point we are going to try to evaluate what happens if I go slightly upstream. So you have this location right here, right? So you got your body coming in this direction. I want to see what happens right there, okay? At some distance, let's say delta, okay? So minus delta. So now what I want to do in my problem is, now the next thing is what happens when x is equal to minus a minus delta, okay? And r is still equal to 0 because I am working on this axis right here. I don't have that r. So if I did that, what you're going to have in the problem, just to show you what's going on, I have a source. I have this source is going this location, okay? Got this source, and this source is given at point minus a. I got my stagnation point right here where I know this is my stagnation point and I know everything is 0. So I am trying to see if I am located at a distance right here, and this distance is actually distance delta. Okay, so the total distance from here to here, that would be x is equal to minus a minus delta. Okay, so if I did that and I expressed and I replaced all this value inside here, you can see that my UR will still be 0 because these are all zeros. But now, however, so immediately UR is equal to 0. But my U of X, let's replace and see what happens. So I have U infinite A. Okay, then I have minus a minus delta plus a, minus a minus delta plus a. All this is squared plus r squared, 3 over 2. And I'm working here at 0. Okay, so this would be 0 minus a minus delta minus a. And this gives you minus a minus delta minus a squared plus 0 squared, 3 over 2. Remember, this is your radius. So when you simplify all this, you get u infinite minus a delta squared, which you can show then, right, that this term you can actually show is going to be less than u infinite. This term will be less than u infinite. So if that's the case, then from here you can immediately show that u of x is going to be less than u infinite if u infinite is less than a over delta squared. Okay, so this is the case, then that's how we know that all the values here are actually u of x is actually less than 0 and ur is equal to 0. Okay, so now we can keep on moving on. Let's see what happens if at the stagnation point we know these are 0. There's no flow coming out or inside that. If you wanted to find that location, how do you find the location? You will set this velocity equal to 0 and you will solve for x. Okay, So if you wanted to stack the value of stagnation point, what you will do is you will set u of x equal to 0, and from u of x equal to 0, then you will solve for the value of x. So if you kept on doing this for each one of the segments and did the same thing from here to here, and then from here, that's how we found that these were actually less than 0, bigger than 0, and bigger than 0. Okay, this is how we find these criteria here. Okay, so now if you wanted to find the stream functions of your problem, stream functions, remember, is given by psi. Psi will be this of the flow plus psi of the source plus psi of the sink. Okay. In other words, and we showed this last time, stream functions squared over 2 minus a x plus a squared plus r squared 1/2 minus x minus a squared plus r squared 1/2 plus a constant. Okay, so if you wanted to find these values now, we know, so for r equal to 0, we know that this value, your psi has to equal to 0. So if you replace all that, you're going to find immediately, that your psi, when you put r equal to 0, gives you the following. It gives you minus a x plus a minus x minus a x minus a, and this gives you 0. And so this is plus a constant, and this gives you 0. So that means from here, your constant is actually equal to 0. So that means that your psi is going to be 0 on the x-axis, for all the x's less than minus on axis minus a, and x equal to bigger than a, okay, and r equal to 0, and when it's constant. And also it's true that this is going to be 0 on the body surface as well. Okay, so one of the things that you have to keep in mind, that your sink and sources are singularities. Okay, these are singularities, and they have to be treated as such. We will do now a couple examples, but before we do the examples, we're going to reduce everything to 2 dimensions and see how that works, and then we do some examples and see what are the real applications of this.